In the ever-evolving world of technology, few fields captivate the imagination quite like quantum computing. It sounds like something from science fiction, a realm where particles can be in two states at once, where computers use probabilities instead of ones and zeros, and where the normal rules of classical physics no longer apply. But this isn't just a dream or a futuristic concept. Quantum computing is real, and every year we're seeing stunning breakthroughs. From new qubit designs to error correction methods, from novel algorithms to claims of quantum supremacy, the pace of innovation is both rapid and fascinating. In this first section, we'll begin by understanding how qubits, the fundamental units of quantum computing, have evolved over time. We'll explore the technical challenges they face, the ingenious designs researchers are developing to overcome those challenges, and why the stability of a qubit is often more important than simply having a lot of them. So take a deep breath. Relax. Let's go slowly. This is a story of curiosity, discovery, and the cutting edge of science. Part 1. What are qubits and why are they so special? To understand breakthroughs in quantum computing, we first need to understand its heart, the qubit. In classical computing, everything is built on bits. A bit can be either a 0 or a 1. Every email, every song, every video, every app is just a collection of bits. Quantum computing is different. A qubit is the quantum version of a bit. But instead of just being a 0 or a 1, a qubit can be in a state called superposition. That means it can be 0, 1, or both at the same time in a probability cloud. You can imagine a spinning coin. While it's spinning, it's not just heads or tails, it's both. Only when you stop it and observe it does it choose a side. That's kind of like a qubit in superposition. And there's more. Qubits can also become entangled. That means if you have two qubits and they are entangled, changing one of them instantly changes the other, even if they're far apart. Einstein called it spooky action at a distance. Superposition and entanglement give quantum computers their incredible potential. They allow them to process massive amounts of data in parallel, but they also create enormous engineering challenges. Qubits are extremely sensitive. Tiny vibrations, heat, even stray electromagnetic waves can cause them to lose their quantum state. This is called decoherence. It's like dropping the spinning coin before you can look at it. It falls over and stops spinning. So how do we make qubits stable enough to build a real computer? That's where the story of innovation begins. Part 2. Types of qubits. A diverse quantum zoo. Over the past decade, researchers have developed many kinds of qubits. Each type has its own advantages and disadvantages. Let's look at the most prominent ones. 1. Superconducting qubits. These are among the most widely used today. Companies like IBM, Google, and Rigetti use them in their quantum computers. Superconducting qubits are tiny loops of metal cooled to near absolute zero. At that temperature, they carry electrical current with no resistance. These loops behave like artificial atoms and can be manipulated with microwave pulses. Pros. They are relatively easy to manufacture using existing semiconductor technology, and we've built systems with dozens or even hundreds of these qubits. Cons. They are fragile. Decoherence happens quickly, sometimes in microseconds. Also, errors can build up rapidly unless corrected. 2. Trapped ion qubits. These use individual atoms suspended in space using electromagnetic fields. Each ion acts as a qubit, and lasers are used to control and entangle them. Companies like IonQ and Honeywell are pioneering this approach. Pros. These qubits have very long coherence times. They're incredibly stable. Cons. They are slow. Manipulating ions takes time, and scaling up is difficult. Imagine trying to control hundreds of tiny atoms with dozens of precise lasers. 3. Photonic qubits. These qubits use particles of light, photons, to encode information. Because light doesn't interact with its environment easily, photons are naturally resistant to decoherence. That makes them promising for long-distance quantum communication and some types of computing. Pros: high stability, fast transmission, and the potential for integrating into fiber optics. Cons: performing logic operations on photons is tricky. Creating entanglement between them requires delicate setups. 4. Topological qubits. This is the holy grail for some researchers. Topological qubits are theoretical constructs based on the mathematics of knots and braids. Microsoft has invested heavily in this approach. The idea is to store information in the topology of certain particles so that small disturbances don't affect the data. Pros: in theory, they could be extremely robust and resistant to errors. Cons: they're still not proven in practice. No one has fully demonstrated a working topological qubit yet. 5. Spin qubits in silicon. These qubits use the spin of individual electrons trapped in silicon. Since they're built on silicon, they might be easier to integrate into existing chip manufacturing techniques. Intel and academic labs have been pushing this forward. Pros: potential for large-scale integration, long coherence times. Cons: very difficult to manufacture precisely. Still in early stages. As you can see, there isn't one right type of qubit yet. Different designs are better for different tasks. Some are fast, others are stable. Some are easier to control, others are hard to build. This diversity is a strength. It means the quantum field is rich with possibilities, but it also creates a challenge. Which path leads to a truly scalable, reliable quantum computer? Part 3. The challenge of error correction. One of the biggest hurdles in quantum computing is error. Because qubits are so delicate, they're constantly subject to interference. Even the best systems today have error rates around 1% per gate operation. That might sound small, but in a quantum algorithm requiring thousands or millions of operations, even tiny errors add up fast. This is where quantum error correction comes in. But here's the problem. You can't just copy a qubit the way you copy a bit in classical computing. The no-cloning theorem in quantum mechanics says you can't make an exact copy of an unknown quantum state. Instead, quantum error correction encodes a single qubit's information across multiple physical qubits. This is similar to how we use RAID systems in hard drives. Multiple disks work together to store a single file safely. The most famous approach is the surface code. It spreads one logical qubit across a lattice of physical qubits. Errors can be detected by measuring certain check qubits without disturbing the actual data. To give you a sense of scale, to store one useful logical qubit reliably, we may need 1,000 or more physical qubits. This is why having 100 qubits is exciting, but not nearly enough for real-world applications. Until we can correct errors reliably, quantum computers will struggle to scale. That's why researchers are working on reducing gate errors in hardware, improving error correction codes, developing fault-tolerant designs where the computer keeps running even if parts fail. In 2023, IBM announced a big step forward, demonstrating the ability to detect and correct errors in real time on a small quantum processor. This isn't full fault tolerance yet, but it's a major milestone. Some researchers are also looking at error mitigation instead of correction. This means accepting that errors will happen, but adjusting algorithms to work around them. Others are exploring noise-resilient algorithms, quantum programs that are naturally more tolerant of small errors. In short, error correction isn't just a feature, it's a requirement. And advances in this area are key to unlocking the power of quantum computing. Part 4. The race to quantum supremacy. One of the most exciting and controversial milestones in quantum computing is quantum supremacy. This is the point where a quantum computer performs a task that no classical computer could do in any reasonable amount of time. In 2019, Google claimed to have achieved this. They used their 53-qubit Sycamore processor to perform a random number sampling task in 200 seconds. They estimated that a supercomputer would take 10,000 years to do the same. It was a bold claim, and it sparked a lot of debate. IBM challenged the number, saying a classical machine could do it in a few days, not 10,000 years. Others pointed out that the task Google chose wasn't practically useful. It was more like a benchmark than a real application. Still, the event marked a turning point. It showed that quantum machines were starting to outperform classical ones in narrow tasks. Since then, other companies and labs have made similar claims. Some focus on solving optimization problems, others on simulating quantum systems, tasks where quantum computers should eventually excel. But the bar keeps rising. Today, people talk not just about supremacy, but about quantum advantage, doing something useful, better, faster, or cheaper than classical methods. Closing thoughts for Section 1. We've come a long way in this first section. We've learned what qubits are, why they're so powerful, and what makes them so difficult to control. We've explored the different types of qubits being developed and the trade-offs of each. We've seen how error correction stands as one of the biggest challenges, and how researchers are racing toward the goal of practical, scalable quantum computing. In the next section, we'll dive into the algorithms, the quantum brains behind the hardware. We'll look at how Shor's algorithm can break encryption, how Grover's search can speed up databases, and how new breakthroughs are expanding what quantum computers can do, even with today's noisy systems. Take a deep breath. Let the ideas settle. We're only just beginning the quantum journey. In the ever-evolving world of technology, few fields captivate the imagination quite like quantum computing. It sounds like something from science fiction, a realm where particles can be in two states at once, where computers use probabilities instead of ones and zeros, and where the normal rules of classical physics no longer apply. Part 1. Shor's algorithm, cracking the code. Let's start with the most famous quantum algorithm of all, Shor's algorithm. In the early 1990s, a mathematician named Peter Shor developed an algorithm that could do something astonishing. It could factor large numbers exponentially faster than the best-known classical methods. Why does that matter? Because modern encryption, like RSA, which secures most of the internet, relies on the difficulty of factoring large numbers. Classical computers take years or centuries to break these codes, but Shor's algorithm can do it in hours or even minutes on a powerful enough quantum computer. It was a wake-up call. Suddenly, quantum computing wasn't just a scientific curiosity. It was a cybersecurity threat. Governments, banks, and tech companies began to take notice. But there's a catch. Shor's algorithm only works if you have a large, stable quantum computer with thousands of logical qubits. We don't have that yet. The biggest quantum machines today can't run Shor's algorithm at useful sizes. They can factor small numbers like 21 or 35, but not the 2048-bit numbers used in real encryption. Still, it's a proof of concept, and it shows that quantum computers can do things classical ones simply cannot. In preparation, governments and companies are already developing post-quantum cryptography, new encryption methods designed to resist quantum attacks. Shor's algorithm didn't just shake up math, it reshaped the entire cybersecurity landscape. Part 2. Grover's algorithm. Speeding up the search. Next comes Grover's algorithm, developed by Love Grover in 1996. This one tackles a different kind of problem, searching through unsorted data. Imagine you have a huge phone book and you're looking for one name. With a classical computer, you'd have to check entries one by one. On average, you'd need to check half the list, but Grover's algorithm can do it in square root of the time. So instead of 1,000 steps, it might take only 32. That's not as dramatic as Shor's exponential speed up, but it's still a big deal. and it applies to a wide range of problems, like password cracking, database searching, constraint satisfaction problems. Grover's algorithm is also quantum safe in a different sense. It sets a lower bound on how fast quantum computers can solve certain problems. This helps researchers design stronger algorithms and defenses. And unlike Shor's algorithm, Grover's algorithm is more forgiving. It doesn't require a perfect quantum computer. In fact, some versions can work on today's noisy intermediate-scale quantum, NISQ, devices. Let's pause here for a moment. Shor's and Grover's algorithms aren't just mathematical tricks. They represent two categories of quantum advantage. Shor's shows us where quantum completely outclasses classical. Grover's shows us where quantum gives a valuable, if limited, boost. Together laid the foundation for the quantum algorithm revolution. Part 3, Quantum Simulation, Chemistry, Materials, and Medicine. One of the most promising and least controversial applications of quantum computing is quantum simulation. Here's the idea. Nature is quantum. Atoms, molecules, and chemical reactions follow the laws of quantum mechanics. But simulating those laws on a classical computer is incredibly hard. For example, simulating a small molecule like caffeine might require more bits than there are atoms in the universe. Why? Because each electron interacts with every other in ways that create an exponential explosion of possibilities. But a quantum computer can simulate quantum systems naturally. It speaks the same language as the particles it's simulating. This opens up incredible possibilities: drug discovery, modeling how molecules bind to proteins at the quantum level, material design, finding new superconductors or lightweight, ultra-strong materials, energy research, simulating efficient catalysts for hydrogen production or carbon capture, climate modeling, understanding complex chemical interactions in the atmosphere. In fact, chemistry may be the first area where quantum advantage becomes practical. Several companies like Quantinuum, Zapata, and PsiQuantum are focusing heavily on this area. They're building platforms to run chemical simulations on early quantum hardware, often in hybrid mode, using classical and quantum processors together. In 2020, researchers used a quantum computer to simulate the energy levels of a simple molecule, beryllium hydride, more accurately than ever before. It's just the beginning, but the path is clear. Quantum computers may not break every code, but they could unlock the secrets of life and matter itself. Part 4, Quantum Machine Learning. AI meets quantum. What happens when we combine two of the most exciting technologies in the world? Quantum computing and artificial intelligence. This emerging field is called quantum machine learning, QML, and it's full of potential. Let's break it down. Classical machine learning uses lots of data to train algorithms, like recognizing images or predicting stock prices. But as the data sets grow, so do the computing needs. Quantum computing might help in several ways. Faster training. Some quantum algorithms can speed up the linear algebra behind machine learning. Feature space expansion. Quantum states can encode data in high-dimensional spaces, potentially capturing complex relationships. Quantum data. In fields like quantum chemistry or physics, the data itself is quantum. Classical computers struggle to analyze it, but quantum ones can do it natively. There are already some promising examples. Quantum support vector machines, quantum neural networks, variational quantum classifiers. Most of these are still experimental, but the idea is powerful. Use quantum processors to process, learn from, and even generate quantum data. IBM, Google, Xanadu, and many startups are racing to create quantum AI toolkits. The hope is that one day, quantum-enhanced machine learning will surpass classical techniques, not just in speed, but in intelligence. We're not there yet, but the convergence of AI and quantum computing is one of the most exciting frontiers in tech. Part 5, Hybrid Quantum Classical Algorithms, the Era. Here's an important reality check. Today's quantum computers are still small, noisy, and imperfect. We call this the NISQ era, noisy intermediate scale quantum. That means we can't run large quantum programs yet. But we can do something clever, split the work. In a hybrid algorithm, the quantum computer does what it's good at, manipulating complex quantum states, and the classical computer does everything else. Optimization, iteration, control. Some popular hybrid algorithms include VQE, variational quantum eigensolver, used for finding the ground state energy of molecules. QO, quantum approximate optimization algorithm, tackles optimization problems like scheduling or logistics. Variational classifiers, used in quantum machine learning. These algorithms are designed to work on noisy hardware and often require only a few qubits. That makes them perfect for today's devices and a bridge to the future. For example, VQE has already been used to simulate the behavior of lithium hydride, relevant to battery chemistry. That's something classical computers can't do efficiently at high precision. Hybrid algorithms represent the path forward during this transitional period. They're like training wheels, helping us ride the quantum bike before we can sprint. Part 6. New algorithms and breakthroughs. Quantum computing is still young, but new algorithms are being developed all the time. Here are a few exciting areas. 1. Quantum annealing. Companies like D-Wave use a special kind of quantum system that solves optimization problems by slowly evolving toward a low-energy state. It's not a universal quantum computer, but it's useful for scheduling airline flights, designing car parts, optimizing supply chains. Recent results show quantum annealers outperforming classical heuristics on certain tasks. It's not full quantum supremacy, but it's practical. 2. Quantum Fourier transform, QFT. This is a key building block used in many quantum algorithms, including Shor's. It's the quantum version of the fast Fourier transform and allows for powerful signal analysis and pattern detection. 3. Hamiltonian simulation, used to model physical systems. This could be the key to unlocking new physics and material science insights. Companies like Rigetti and academic groups are actively developing tools to simulate complex systems using quantum logic. Quantum walks. These are the quantum version of random walks, used in graph theory and optimization. Quantum walks can spread faster across networks, leading to new search and decision-making algorithms. In all of these areas, new papers are published almost every week. The pace is rapid, the creativity is astounding, and the future is wide open. Closing thoughts for Section 2. Quantum computers are more than just strange hardware. Their true power lies in the algorithms, the programs that make them useful. From factoring giant numbers with Shor's algorithm to searching databases faster with Grover's algorithm, from simulating molecules to training AI models, quantum algorithms are transforming what we think is possible. And they're doing it today on small, imperfect machines with the help of hybrid strategies and clever workarounds. We're still early in the journey, but the software is evolving alongside the hardware, and every new algorithm brings us closer to the full potential of quantum computing. So far, we've explored the essential building blocks of quantum computers, qubits, and examined their delicate nature and evolving designs. Then we dived into the fascinating world of quantum algorithms, from code breaking to chemistry, optimization to artificial intelligence. Now we turn our attention to the real world, because quantum computing is no longer just a lab experiment. It's moving out of the research papers and into industry, government policy, international rivalry, and everyday technologies. In this section, we'll explore the global race to lead in quantum computing, the industries most likely to benefit first, the ethical questions this technology raises, and what the future might look like if we get it. As always, breathe slowly. There's no rush. Let's explore the horizon of the quantum era together. Part 1. The Global Quantum Race. quantum computing isn't just a science project, it's becoming a geopolitical priority. Around the world, governments and corporations are investing billions to gain an edge in this emerging field. United States. The U.S. leads in terms of private sector innovation. Major companies like IBM, Google, Microsoft, Intel, Amazon, and many startups, Rigetti, IonQ, PsiQuantum, Xanadu, are all working on different quantum platforms. In 2018, the U.S. passed the National Quantum Initiative Act, launching a coordinated $1.2 billion effort to boost research and talent development. Agencies like the Department of Energy, DARPA, and NASA are all involved. Private-public partnerships are emerging fast, and universities like MIT, Caltech, and Stanford are producing a new generation of quantum researchers. China views quantum computing as a strategic technology. It has invested heavily in quantum research and built massive infrastructure to support it. In 2020, Chinese researchers claimed to achieve quantum supremacy with their photonic processor, Zhujiang, solving a problem faster than any supercomputer could. While the application was narrow, it demonstrated serious capability. China's National Laboratory for Quantum Information Sciences is reportedly funded with billions of dollars. The country also made headlines for quantum satellite experiments, pushing the boundaries of secure quantum communication. European Union. The EU is also investing through the Quantum Flagship Program, a €1 billion 10-year initiative. Countries like Germany, France, the Netherlands, and the UK are building collaborative research hubs focusing on hardware, software, and applications. Companies like IQM, Finland, QTech, Netherlands, and Oxford Quantum Circuits, UK, are making waves. Others. Canada has been a pioneer, thanks to companies like D-Wave and research institutions like Perimeter Institute and University of Waterloo. Australia has made remarkable strides in silicon spin qubits, led by University of New South Wales. Japan, South Korea, and Singapore are also investing steadily. This isn't just scientific competition, it's about economic power, cybersecurity, and national security. In the future, the country or company that controls quantum computing may control critical infrastructure, AI, medicine, and even defense. We are watching a modern version of the space race, quiet, complex, and incredibly high stakes. Part 2. Real-world applications on the horizon. While quantum computers aren't replacing classical computers anytime soon, we are beginning to see real-world use cases emerge. Here are some industries that could see benefits first. 1. Pharmaceuticals and drug discovery. As we discussed earlier, simulating molecules is one of quantum's killer apps. Companies like Roche, Pfizer, and Biogen are partnering with quantum startups to speed up drug discovery. Quantum simulations can help understand how a drug binds to a protein, saving years of trial and error. Point 2. Finance and risk modeling. Banks like Goldman Sachs, JP Morgan, and HSBC are exploring quantum computing to optimize portfolios, detect fraud, and simulate market behavior under uncertainty. Quantum algorithms could improve Monte Carlo simulations, which are widely used in pricing derivatives and assessing risk. 3. Logistics and optimization. Quantum computers are ideal for solving complex optimization problems. Think delivery routes, airport traffic, supply chains. Companies like Volkswagen, Airbus, DHL, and FedEx are testing quantum approaches to reduce costs and emissions. 4. Material science and batteries. Designing new materials, such as lightweight metals, solar cells, or superconductors, requires understanding atomic interactions. Quantum simulations may unlock the next generation of batteries, or even room temperature superconductors. Toyota, BASF, and ExxonMobil are among the industry leaders exploring this potential. 5. Cybersecurity. Quantum will both break and make encryption. On the one hand, quantum computers could render current public key cryptography obsolete. On the other, quantum key distribution, QKD, offers ultra-secure communication, already being tested via satellites and fiber networks. Governments and corporations must transition to post-quantum cryptography, ensuring that data encrypted today isn't vulnerable to tomorrow's quantum attacks. 6. Artificial intelligence. Quantum machine learning is still in early stages, but combining quantum processors with classical AI models could lead to new breakthroughs in training speed, model quality, and data analysis. Quantum startups are working on custom processors for AI workloads, aiming to bridge the best of both worlds. The common thread? These are not theoretical dreams. These are experiments, pilots, and trials happening now. Real value is emerging, one quantum bit at a time. Part 3. Ethical questions and quantum inequality. With great power comes great responsibility. As quantum computing advances, it raises profound ethical and social questions. 1. Data privacy and surveillance. If quantum computers can break today's encryption, what happens to medical records, financial data, or personal emails encrypted years ago? There is a harvest now, decrypt later threat, where adversaries collect encrypted data now, planning to break it once they have the quantum power. This calls for urgent upgrades to secure systems with new quantum-resistant algorithms. 2. Concentration of power. Quantum computing is expensive. The hardware is exotic, the talent pool is limited, and the early benefits may be captured by a few corporations or nations. Will this lead to a new digital divide? Could developing countries be left behind in the quantum revolution, just as they struggled to access classical computing in the past? Efforts must be made to share quantum resources through cloud access, education, and open collaboration. 3. Weaponization. There are concerns that quantum computing could be used for offensive cyber attacks, crippling encryption, simulating advanced weapons, or automating warfare. International agreements may be needed like we had for nuclear arms to ensure quantum remains a tool for peace, not destruction. 4. Intellectual property and patents. Quantum algorithms and hardware designs are being patented rapidly, but should foundational algorithms like Shor's or VQE be owned, we need thoughtful frameworks to balance innovation with open science. 5. Environmental costs. Quantum systems require cryogenic cooling, specialized materials, and energy-intensive infrastructure. As we scale up, we must consider their environmental footprint. Can we make quantum computing green from the start? These questions don't have simple answers, but they are vital to ask before quantum becomes mainstream. Part 4. The quantum workforce and education. Quantum computing isn't just for physicists anymore. As the field grows, we need engineers, programmers, designers, ethicists, teachers, and business leaders who understand quantum concepts. That's why companies and universities are launching quantum boot camps, online courses like IBM's Qiskit and MIT's XPro, quantum programming languages like QCirc and Qiskit, collaborative tools, and open source libraries. Students today may write the quantum apps of tomorrow, and companies that invest in quantum literacy will gain a strategic edge. Even if you're not a quantum physicist, understanding the basics of superposition, entanglement, and quantum logic will soon be as important as knowing how to use a smartphone. The quantum workforce is being built now. Part 5. A glimpse into the quantum future. Let's end this journey by imagining what a quantum-enabled world might look like in 10 to 20 years. Drug discovery becomes faster, cheaper, and more personalized. Global supply chains adapt in real time using quantum-optimized logistics. Climate models run at unprecedented detail, helping us fight global warming. Financial crises are better predicted and averted. AI systems understand complex data patterns we can't yet imagine. New materials unlock space travel, energy breakthroughs, and biomedical marvels. Ultra-secure communication protects privacy across borders. Education systems offer quantum training to everyone, everywhere. The quantum future isn't about replacing classical computers. It's about augmenting them, solving problems we couldn't even touch before. It's about working with uncertainty, not against it. It's about embracing probability, complexity, and the strange beauty of the quantum world. And above all, it's about possibility. Final thoughts. Quantum computing is one of humanity's boldest scientific quests. It challenges our assumptions, tests our engineering skills, and offers new hope for solving some of the world's most complex problems. In these 3 sections, we've explored the evolution of qubits and the need for stability, the rise of powerful algorithms and their practical potential, the global race, ethical challenges, and vision for the quantum-enabled world. This is not the end. This is just the beginning. Keep asking questions, stay curious, and remember, the future is quantum, not just in technology, but in thought. Thank you for listening.